Look up at the night sky. It's filled with countless tiny points of light, isn't it? We call them stars. They seem so small and peaceful from down here on Earth, but in reality, they are gigantic burning balls of gas, incredibly far away. Each star is a sun, much like our own, and they have a life story. They are born, they live for billions of years, and eventually they die. This cosmic story, the life cycle of a star, is one of the most magnificent tales the universe has to tell. It's a story of creation and destruction, of gravity and light that has been unfolding across the cosmos for longer than we can possibly imagine. It connects everything, including us. The story of every star begins in a place that might sound a bit strange. A giant cold dark cloud. These are not the fluffy white clouds you see in our sky. These are vast clouds of gas and dust floating in the emptiness of space known as nebulae. They are immense, stretching for light years across the galaxy, and they are the cosmic nurseries where stars are born. Inside these enormous clouds, the primary ingredients for making a star are hydrogen gas and tiny specks of dust. For a very long time, these clouds just drift peacefully through space, waiting for something to happen, a trigger to start the incredible process of stellar birth. So, what kickstarts this process? It often begins with a little push, a shockwave from a nearby exploding star. A supernova, or the gravitational pull from a passing galaxy, can disturb the quiet cloud. This disturbance causes parts of the nebula to clump together. As more and more gas and dust gather in one spot, gravity takes over. Gravity is the force that pulls things together, and in these clouds it starts pulling the material inwards, tighter and tighter. The clump begins to shrink and spin, growing denser and hotter at its core, like a cosmic snowball rolling downhill and getting bigger and bigger. This dense, hot ball of contracting gas is called a protostar. It's not quite a star yet, but it's on its way. It's a baby star, still gathering material from the surrounding cloud and growing in size and temperature. The core of the protostar gets incredibly hot, reaching millions of degrees Celsius. It glows with a reddish light, but it's still hidden deep inside its dusty cocoon, invisible to our normal telescopes. It can take millions of years for a protostar to gather enough mass and for its core to become hot enough to take the next monumental step in its life, the step that will finally turn it into a true star. The moment a star is truly born is a moment of incredible power. When the core of the protostar becomes hot enough and the pressure becomes immense, something amazing happens. It's called nuclear fusion. This is the process where tiny particles of hydrogen gas are squeezed together so tightly that they fuse to form a new element, helium. This process releases a tremendous amount of energy in the form of heat and light. This outward push of energy is what stops the star from collapsing any further under its own gravity. It creates a perfect balance, a state of equilibrium that will define the star for most of its life. Once nuclear fusion begins, the star leaves its nursery and enters the longest and most stable phase of its life, the main sequence. Our own Sun is a main sequence star, and it has been in this phase for about 4.6 billion years. During this time, the star shines steadily, converting hydrogen into helium in its core. The color and brightness of a main sequence star depend on its mass. Smaller, less massive stars are cooler and glow with a reddish-orange light, like Proxima Centauri. They burn their fuel very slowly and can live for trillions of years, far longer than the current age of the universe. On the other hand, stars that are much more massive than our Sun are incredibly different. They are hotter, bigger, and burn with a brilliant blue-white light. Think of a star like Rigel in the constellation of Orion. These cosmic giants are the rock stars of the universe. They live fast and die young. Because they are so massive, their gravity is much stronger, causing the nuclear fusion in their cores to happen at a much faster rate. They burn through their hydrogen fuel in just a few million years, a mere blink of an eye in cosmic terms, before their dramatic lives come to an end. So for billions of years, a main sequence star like our Sun will continue this calm and steady existence. It is a cosmic engine, continuously turning mass into energy according to Einstein's famous equation E=mc². This energy travels from the core to the surface and radiates out into space, providing light and warmth to any planets that might be orbiting it. This stable period is crucial as it allows for the possibility of life to develop on planets like Earth. The main sequence is the long, quiet adulthood of a star, a period of balance before it begins to enter its old age. Every star, no matter how large or small, has a limited supply of hydrogen fuel in its core. Eventually, after billions or even trillions of years, this fuel will begin to run out. When this happens, the star's long, stable life on the main sequence comes to an end, and it enters its old age. The delicate balance between gravity pulling inwards and the energy from fusion pushing outwards is broken. Without the outward pressure from hydrogen fusion, the core starts to collapse again under its own weight. This collapse marks the beginning of the end for the star, triggering a series of dramatic changes. As the core contracts, it becomes even hotter and denser than before. This intense heat causes the outer layers of the star to expand enormously like a giant balloon. The star swells up to hundreds of times its original size, transforming into what astronomers call a red giant. Our own sun will become a red giant in about 5 billion years. When it does, it will expand so much that it will swallow the inner planets, Mercury and Venus, and possibly even Earth. Although the star's surface is expanding, it is also cooling down, which is why it glows with a reddish-orange color. Inside the red giant, the star gets a temporary new lease on life. The collapsed core becomes hot enough to start fusing the helium that was created during the main sequence. This new fusion process creates heavier elements like carbon and oxygen. For a while, the star finds a new temporary balance, burning helium in its core. However, helium is a less efficient fuel than hydrogen, and this phase doesn't last nearly as long. The star becomes unstable, pulsating in size and brightness as it struggles to maintain its equilibrium. It is a star in its final turbulent stages of life. For massive stars, this process is even more spectacular. They don't just become red giants, they swell up into even larger stars called red supergiants. A famous example is Betelgeuse, the bright red star in Orion's shoulder. These supergiants are truly colossal, so large that if one were placed where our sun is, its outer layers could extend past the orbit of Jupiter. Inside their cores, the fusion process continues to create heavier and heavier elements, going from helium to carbon, then to neon, oxygen, silicon, and finally to iron. This is the star's last act before its final cataclysmic demise. The way a star dies depends entirely on its mass. For average-sized stars like our Sun, the end is relatively peaceful. After the red giant phase, when the helium in the core is used up, the star doesn't have enough mass to create the pressure needed to fuse heavier elements. The star's outer layers drift away into space, creating a beautiful glowing shell of gas called a planetary nebula. These nebulae are some of the most stunning objects in the night sky, intricate structures of gas illuminated by the dying star at their center. They are the star's final gentle breath. Left behind at the heart of the planetary nebula is the collapsed core of the star, a tiny, incredibly dense object called a white dwarf. A white dwarf is about the size of the Earth but contains the mass of the Sun. It is one of the densest objects in the universe. It no longer produces energy through fusion. It's simply the hot, glowing ember of a star that has run out of fuel. Over an incredibly long time, billions and billions of years, the white dwarf will slowly cool down and fade away, eventually becoming a cold, dark object known as a black dwarf, a dead star drifting through the cosmos. The death of a massive star, however, is anything but peaceful. It is the most violent and energetic event in the universe. When a massive star creates iron in its core, it has reached a dead end. Fusing iron doesn't release energy, it consumes it. The core collapses catastrophically in a fraction of a second and the star implodes. The outer layers then come crashing down onto the core and rebound in a titanic explosion called a supernova. For a few weeks, the supernova can outshine an entire galaxy, blasting heavy elements forged inside the star out into space. What remains after the supernova also depends on the star's initial mass. If the star was very massive, the core collapses into a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons. If the star was exceptionally massive, gravity wins the final battle completely, and the core collapses forever into an object from which nothing, not even light, can escape. A black hole. These stellar deaths, especially supernova, are incredibly important. They scatter the elements necessary for life, carbon, oxygen, iron, across the galaxy, seeding the next generation of stars and planets. We are quite literally made of stardust.